All right, so we have been working on Chapter 7. We're doing quantum theory and atomic structure. And so we introduced the electromagnetic spectrum in our last lecture, electromagnetic spectrum. We talked about the speed of light is the wavelength times the frequency. And we also introduced energy equals h nu, which is Planck constant, times the frequency. We defined what a wavelength of light looks like. This is the wavelength, and we also talked about what frequency means. We also said that it was s-1 or hertz, or 1 over s for seconds. We talked about where to find the speed of light, and that constant is on your periodic table, and you can round that to 3.00 times 10 to the 8th, and that's meters times negative second. And then if you want to do something like calculate the frequency is nu, then nu equals c over lambda. You notice that if you have a higher frequency, you have a lower wavelength, and also energy is, so if you have a higher frequency, you also have a higher energy, because those are directly proportional. So here, if we solve for frequency, you would do 3.00 times 10 to the 8th meters reciprocal seconds. And then frequency here, in nanometers, you're going to have to convert nanometers to meters, because that's what speed of light is. So to do that, you got to take 126 nanometers, and then you would divide that by nanometers into meters, and that should be 126 divided by it's like 6 zeros. 1, 2, 3, 4, 5, 6, 1, 2, 6. And so that's meters. So now we divide by 3.00 to the 8th divided by the meters, and you should get the frequency then would be 2.38 times 10 to the 15th, and this is meters, and so these cancel out, and you're left with reciprocal seconds. So that would be B. Now, this lecture, I would recommend reading the textbook. There's a lot of kind of physics, and I will just be giving such a brief overview of this topic. It is very fascinating, but like I said, you need to read the textbook and spend some time doing that. I'm going to tell you which formulas that you're going to have to work problems, and which ones we will just talk about, or I'll say read on your own, meaning you won't see it on a quiz or an exam. Okay, so let's talk about light. We're talking about light. We've talked about the electromagnetic radiation. And so in the early 1900s, it was a lot of work was done to understand light. And what we learned is that light and the electron, so I think light is an electron, and the electron is both a wave and a particle. Now, during that time, people are like, oh, that can't be true. You either are a wave or you're a particle. But during the turn of the century, the 1900s, a lot of studies between Max Planck, and I told you about him, he's Planck's constant, Einstein, and Niels Bohr, all kind of, they were the three scientists at the time, and they did lots of different studies to prove that light is also a wave and a particle. And what does this mean? Well, a wave will come and when it hits a surface, so wave goes through like a medium of air, when it hits a surface, it has an angle of refraction. It bends. And if a particle hits a surface, it has to go through a slit, and then and that speed can change when it goes through. That's what they're showing you here. You see this little slit right here, and so what happens is if you have light that goes through, once it hits the slit, then it does a diffraction, and then it changes the wave pattern. If you have a beam of particle, these are all blocked because they get absorbed or diffracted on by the material if it's a particle, but if you have a little slit in there, it can keep going through. But notice it doesn't change the wave. And so studies were done to take light, and they would put it through these little slits, and then they would try to see on film, they would catch on film this diffraction pattern. And so you see that when these waves could combine, and that would be a constructive phase, and then they would increase. So this amplitude gets higher when you add these two waves together. So that's the amplitude. Or they could be destructive and they out of phase, and they're going to cancel each other out. And so then the amplitude gets smaller. So that's what happens if you have like two diffraction pattern slits, and these waves that then are coming out on the other side, they can either combine and get a brighter area, or they can go dark, which is destructive. So this was the study done. And so what was learned from this study is that light is both a particle and a wave. And so you think about waves, you hear sound waves, so we can hear sound waves. And you think about water. And if you skip a particle, like such as a rock, on a water, it generates these waves, right? So that's what we think of when we see a wave. A particle, you would do different formulas to just study a particle. And so this formula here, E equals NH nu, is more about it combines the particle and the wave. And so that's what N is. N is like a number. It's just a number. So it's a number of photons. But we're just going to assume N is equal 1. And that's why I just have energy equals H nu. H is Planck's constant because Planck is the scientist that came up with this formula. You have this number for nu on your periodic table. And so what this is showing you that there is an energy associated with this wave. See, we know V is nu, which is frequency. And we think of frequency, we think of waves. Okay, so that's the wave, and it's the number of waves that pass through a point in 1 second. Okay, but then when we think of energy, energy is like a particle. So if you have a baseball, and you throw a baseball, it has a certain amount of energy. Okay, so particles can have this energy. And so this was studied, and what came out of this was called black body radiation. And you've seen this, but you might not be aware of it. So like when you heat up a metal, so if you take a piece of metal and you heat it up, and it changes colors, okay? So it changes colors. And you know that color is related to frequency, the electromagnetic radiation. You know now that a certain color, so if you see red, you know that it has probably, I'm going to look at the electromagnetic spectrum, you know that it has about 750 nanometer wavelength. So it has this wavelength of that magnitude. But now we know that this metal has a change of temperature. And we know that temperature is related to energy, right? Because what is energy? Energy is in joules, and we know that that is heat. And we know that from the last chapter, the delta E equals the delta H when at constant pressure. So we have simplified formulas to say, okay, the heat is energy in a lot of systems. And so now this is showing you that energy can be related to the wave, and then this is light. Okay, so these are some examples of color changes that you see, and this is energy. E equals h nu. So this is the black body radiation, and the temperature will cause, and this ejects a particle. Okay, so this is ejecting light. That's why we see it. Light is traveling with a certain wavelength through this medium, right? And so it's ejecting that energy. So any object, including atoms, can emit or absorb certain quantities of energy. So energy is quantized. So energy, it's a number, right? It's quantized. See, this is the birth of quantum mechanics, if you've ever heard of quantum mechanics. And quantum mechanics, is a study of light. And light is if you travel in quantum. So if you travel in quantum, you could basically snap your fingers and you might be here and then you're there, okay? You're never in between, okay? So you're never in between here. You're never in this space. That's what it means to travel in quantum. Now we travel in continuum. Continuum means if we are here and we want to go there, at some point we might be in between in a time and space. And the reason why we travel in continuum because we have mass. And when you have mass, you can't travel in quantum. But light is, think of it like an electron. Electron basically has essentially, we say the mass is 0. Okay, so electrons travel in quantum. And so, and the reason why this helped us understand the model of the atom. So you have your protons, and then you have your neutrons. I'll just put those like that in the nucleus. But then you have your electrons out here, okay? And you have your electrons here, and so Bohr did a lot of studies on this to understand that the electrons are quantized in energy levels outside the nucleus. And so that's what this work kind of led to. And so this is E equals h nu, and we also have to be able to take the wavelength, and we can solve C equals lambda nu, solve for nu equals C over lambda, and that's how you put that in for nu to get this. We will basically do everything where n is one quanta of energy. Okay, so when you shine light on a metal object or just some kind of object, so you could have metal, you know, we could have aluminum, and you shine your light. So we shine the light on the aluminum metal. So this is light. That energy, there's energy. Energy equals h nu. So there's energy associated with this frequency of light, and it hits the metal. Now the metal can turn red, right, or a certain color, doesn't have to be red, and then it can eject energy. And if it ejects energy, that's equals h nu. And and it can be bundles of energy. So if you don't have intensity, then you're not going to have a lot of injection. So there is a threshold of frequency there to be able to eject a photon. And so studies were showed done in these vacuum with different metals to eject an electron. Now, what you need to be able to do is solve problems like this for your exam and quizzes. I think we did this in, if we did this in class or not. So E equals H nu, and so then C equals lambda nu, and you need to solve for lambda here. I mean, solve for nu, so you can put this in. So nu equals C over lambda. You're going to put that in for that. So you're going to change your equation to E equals H, and then put this in C over lambda because you're given wavelength. You know that because it's centimeters. Wavelength is lambda, which because we have C, what is C? 3.00 times 10 to the 8th meters reciprocal seconds. You get that on your periodic table. What is H? That's Planck's constant. 6.626 times 10 to the negative 34 joules times second. You get that also on your periodic table. And see this, this correlates joules, which is your energy, and your frequency. There's your seconds. But you see that we have to get our wavelength in meters, and we have it in centimeters. So you want to take 1.20 centimeters, and then you need to convert centimeters, which is 100 centimeters, into 1 meter. And that gives you 1.20 divided by 100. That gives you 0.012 meters. And then so you plug it in, you would say E equals 6.626 times 10 to the negative 34 joules second times 3.00 times 10 to the 8th meters reciprocal seconds divided by 0.012 meters. The meters cancel out, the reciprocal seconds cancel out, and you're left with joules. And let's make sure that we can do that on our calculator because you are dealing with exponents and negative exponents, and you don't want to get that wrong. So 6.62 to the negative 34 times 3.00 second e to the 8th divided by 0.012. And I did get this number. See if you got that number. So that's how much energy is associated with when you use a microwave oven to heat a metal. And that's the wavelength of radiation from that metal. So let's try another one. How much energy per photon? So we're just going to say photon equals 1. Green light, wavelength of 532. So this is energy. So you want energy equals H nu, and then you're given the wavelength, so you need C equals lambda nu. And then you want to rearrange this equation so you can replace it with nu because you're not given frequency, you're given lambda. So C equals lambda divided by nu, and then you put this in for that equation. So now you have E equals H C over, you want to solve for frequency, I'm sorry, V equals C over lambda. So now we can go, okay, Planck's constant is 6.63 times 10 to the negative 34 joules per second. You can take that all the way out on your periodic table, 6.6261. C equals 3.00 times 10 to the 8th meters per reciprocal seconds. And then here we want to make sure, once again, that our wavelength is in meters, it's in nanometers. So 532 nanometers divided by the 9 zeros here into 1 meter, you get 0.0000000. There's 6 of them, 532 meters. And so now you can do energy equals 6.6261 times 10 to the negative 34 joules second times the speed of light here divided by 0.000000532 meters. Okay, 6.626 to the negative 34 times 3.00 to the 8th divided by 0.000000532. And so the energy associated with this 3.74 times 10 to the negative 19 joules. And so if you have a red light or green light, okay, that's green light. Okay, and then if you have what's the energy associated with, so that's green light. Let's make this green. So this is the green light. That's 532. And then the red light is 635. So we just do this equation here, and we're going to divide by 0.000000. There's 60635 meters. So now we can take 6.6261 to the negative 34 times 3.00 to the 8th divided by 0.00000635, and that is energy equals 3.13 times 10 to the negative 19 joules. So which one has more energy? They're both to the negative 19, so this one's 3.74, this is 3.13. So green has greater energy than red. And the difference is about 0.74 minus 0.13 by 0.61 joules. All right, calculate the energy per photon of light with a wavelength of 650. So E equals 6.6261 times 10 to the negative 34 joules. Second, 3.00 times 10 to the 8th meters reciprocal second, divided by 0.000000650 meter. I wonder if we just did this. Seems close. So the energy equals 3.058 times 10 to the negative 19 joules. So that would be A. All right, so now we're trying to understand, take the energy of light is a wavelength. We've talked about the wavelength. C equals lambda nu. Okay, wavelength. And then we've also talked about the particle. E equals h nu. This is the particle nature of light. And now we're trying to understand when light hits different elements, different materials, okay? It actually gives off these spectra, these line spectra, because if you put this different type of element, so you have mercury, you're going to have to heat these up, okay? So you can put them in there and you put them through a slit here, they give off energy, E equals h nu. That light then goes through a slit, and then what is that frequency? See, this frequency of light has a certain energy associated with it, and that light then can be gone through a prism to give a diffraction pattern, and the light will show a diffraction pattern. And so what's interesting, if you've ever looked at these with different ones, it's kind of cool. If you have mercury in there, you get this diffraction pattern. If you have strontium, you get this one. If you have neon, you get this one. So these different line spectras, here's hydrogen, can tell you which element you have. And that means they're characteristic. So now, what does this mean? Well, this means that the atoms, because we're talking about like what is a hydrogen atom? Well, hydrogen has, we know, one proton, and then it has no neutrons, and then it has one electron. And this one electron will give a certain spectra. And what that means is at this energy, when it has a certain energy, it's here. And then at this energy, which, and it's, these are colors, right? Roy, G, Biv. So if you look at the um, periodic table, anytime you see red, you know red's associated with a certain wavelength of nanometer. Whenever you see blue, you know it's a certain wavelength. And so these wavelengths, there's nothing in between here. You see how this is all black? There's nothing in between here. So the electron is given off these diffraction patterns. And what that means is, and Bohr, Niels Bohr, came up with these stationary states and says each state is associated with a fixed circular orbit of the electron around the nucleus. So when you have hydrogen, which has one proton in the nucleus, and then you have an electron, and you have this energy state. And you're going to learn that the energy state is energy levels, and we're going to talk about quantum, and this is the birth of all of quantum mechanics. But quantum has these energy levels. N is an energy level. And so you can have energy level of N equals 1, and then you can have energy level, which is a circle, N equals 2. You can have energy level of N equals 3. And so these electrons travel in quantum. That means they're never in between here. This is empty space. And so those electrons are never in between this empty space because they do not travel like we do in quantum and continuum. So in the ground state, because there's only one electron, the hydrogen electron is in its first orbital, and that's called N equals 1. You're going to know there's these mathematical work done, and it gives you this thing like this. It's called a psi. So I guess that's the Greek letter. It's like a pitchfork, and psi squared. You would say psi squared is the probability of where you'd find electron. Okay, so if you find, so there's been studies done, and there's 4 numbers that come out of these. There's just pages and pages and pages of mathematics, okay? We don't have to do that. They have computers to do a lot of that now, but we will do the 4 numbers. Well, the 4 numbers for chemistry have been changed to letters, okay? So you're going to end up knowing 4 letters. Even though they're going to call them numbers, they're letters. And each letter has a description, and it describes where these electrons are and how to find the electrons. The reason why we care about this as chemists is because when you have chemical reactions, you're basically taking away electrons or combining new electrons, and that's how you make new materials. So the first thing you see is a hydrogen electron has 1 electron, and when it's in N equals 1, this is the lowest energy level because it's closest to the nucleus. They call that the ground state. Okay, so that might have been in that spectra, that blue. But what happens is that you can get enough energy and bombard this energy that that electron can now go up to an energy level of 2, but it's never in between. And then that's called an excited state. And that's what we'll see in the excited state. And then if you take away the energy, then it falls back down to its ground state. So that's where they're saying when an electron is in an orbit higher than N equals 1, the atom is in an excited state. So when you're doing that study and you're bombarding the energy and you get these different diffraction patterns where you have blue there and then you have a red slit, that is an electron in an excited state. And so that's why you're seeing the different diffraction patterns. And so this is kind of an example of how electrons travel. They travel in quantum. That means they're either in the ground state, or they could be in an excited state, or they can go up to all these different levels, but you're never going to find the electron in between these levels. So if you roll something down the stairs, it's going to be sitting on one of these staircases, and you won't just have it lingering, let's say, in between, because they're particles. This is another way of explaining these diffraction spectrum lines. Um, and so as you can see, n equals 1, and you have different energy levels associated with the when the excited state, they call it, relaxes back to the ground state. Ground state is like low energy. And so you can bombard elements and metals with energy, and you're going to get the color. So you'll get the color because you're going to get an excited state. But then you know if you take away that energy, it's going to go back to its ground state. Now this is important because it's led us to a lot of instrumentation. So this is instrumentation. This is the principles that came out of from Einstein in the early 1900s. So not only did this tell us the structure of the element model, the model of the atom, it also gave us the atomic energy, which is E equals mc squared, which came up with the nuclear bomb. Okay, the nuclear bomb. Have you seen that? That's mass. E is the mass. C is light squared. So the nuclear bomb came out of this energy. And also the instrumentation, we can identify substances. We can identify elements and substances because of these different diffraction patterns. Now, there are some things I'm not going to ask you to work on exams and quizzes, and this is one of them. It's just because the math is a little bit, it can be a little bit more tricky. But these are like if you go from one state to the next state. Okay, so if you go from an excited state to the ground state, what's the energy difference? And this helps you figure that out. Like I said, you're not going to be asked to solve that. And so I left this on here in case you need to refer to this and refer to the studies. You know that it's here, and you can look at your textbook for any kind of homework questions you might get. And that shows you the different energy from going from an excited state to a ground state. And so this is the emission spectrum. This is where we get fireworks. This is where the colors come from. The energy ejects that E equals h nu, and it gets different colors, and these colors show up because they're different energies associated with the wavelength. And so this is shows you sodium, Na, emission spectra. You have, it gets too light in the yellow. This is a spectrometer that can detect what kinds of metals. This is the different kinds of metals. This is atomic absorption. Spectroscopy, you put your sample in there, you hit it with some light. The light gets diffracted into the different wavelength energies, so you can select for just, in this case, if you want that one wavelength energy, E equals h nu, you can select for violet energy, and then we can figure out what that compound is, or that element. You can measure chlorophyll, and then you get different absorption patterns here, and you can see the wavelength. These are called the wavelength max, and you can see those absorption patterns are characteristic of certain substances like chlorophyll. It's like taking a picture, and you see a picture and you see, oh, well, that's so and so. I know that person. That would be a characteristic. Well, when you get these wavelength peaks like this in a chromatogram, you can also figure out what kind of element or compound you have. And it's because of these principles. Okay, E equals mc squared. I just want you to know that. We're not going to, I'm going to ask no mathematical problems on this for our text, or for our test or quizzes. So, but it's good to know that all matter acts as both particles and waves. So guess what? You are a particle, right? You can see yourself as a particle, but you also have a wave associated with you, and you can calculate your wave by your mass. And so this is called the de Broglie wavelength. And you can figure out your wavelength associated with your mass and that speed. And so the reason why we travel in continuum is because of this equation here. And we don't travel fast enough, you see, because of the mass times the speed. So if you increase these, then you decrease our wavelength. We can't travel at the speed of light. So this is a wave. So you think of sound waves. And sound waves will create certain waves. And they're just showing you the principle of waves. They always have to go and have a complete circuit. So this is why certain things are permitted and not. This is trying to get you to understand waves into numbers, okay? So to do these waves, the waves are here, but here, these are called, a thing called nodes. And nodes are zero probability. Probability is psi squared. Probability of finding any kind of wave. Okay, and so what we're going to talk about is electrons are waves, and electrons are particles. But whatever principles we know about waves, we can apply them to the electrons. And so it's just showing you the different masses, and they travel at different speeds, and you can see electron travels at like, what, 5, 9, 1, 2, 3, 4, 5 meters per second, but a baseball travels very slow. And the reason why baseball travels very slow is because it has a lot of mass. Look how much mass it has, and then its wavelength is very small. Like I said, you don't have to work this on exams, but I left it here in case you want to understand. So they're just showing you that you have diffraction patterns with different, when light interacts with metals, or, you know, for like X-rays, and you hit light and light goes through, it's not absorbed in our tissues, but then it is diffracted when it hits bone. We can see different diffraction patterns. Same thing with an electron micrograph. If you hit different materials with these different energies and you magnify them, then you can actually use this technology to see. That's how we get the structures. So classical theory is continuum, and quantum theory is how electrons travel. And so you can see this is merging for energy and matter to be also wave. And so Heisenberg, he was another scientist at the time, said that you can never, it is impossible, not possible to know both the position and the momentum of a moving particle at the same time. You're not going to have to do anything on this, but this is the formula that comes out and says, okay, and this is that box. If you've ever heard people talk about the cat in the box. And so if you study the cat in the box and you see that the cat is over here, and you study this area over here, by the time you go to apply it, the cat is probably moved over here to another area of the box. And so it's impossible to know the momentum, and so that's like the speed, like where it's going and location, and the position at the same time of a moving particle. Because like I said, once you're studying it here, the time has lapsed and now it's over here. So what this is doing, and like you don't, I've just left this for you to look. What this is doing is it's setting you up to understand um, where electrons are. So the goal is to figure the model of the atom. We want to know, we know electrons are outside the nucleus, and now we're going to start studying them like a wave. And so this is your psi squared, and this is kind of how you approach waves. This is just a probability of locating the electron. And it's kind of like the cat in the box. I mean, once you find it over here and it's a moving particle, then it's over here. Okay, so it's impossible to know the location and momentum at the same time. So it's just a probability. So I think you can approach like 90% probability of where you're going to find an electron. And this is called the Schrodinger wave equation. And you're not going to go through that. If you do take quantum, then you get to do a little bit of that. And so all we have is the probability. I think your book has a picture of an apple tree. That was good. Okay, and so this apple tree, where did the apples fall? Okay, so where do the apples fall? And what you find is that you have probably 90% of your apples fall from the tree in this area, and then that would be like 10% out here. And so that's what you're approaching is, so you have this, the nucleus here, and then you have pretty much 90% of your electron density, that's what they call electron density, which is the probability of finding an electron, and that is n equals 1. So you're going to have these different energy levels in which electrons can be, and you'll have energy n equals 2, n equals 3, n equals 4, n equals 5. N is the energy level. And remember I told you there's 4 quantum numbers? But I said they're actually letters, okay? So n is one of the quantum numbers, and it is energy level of the probability where you're going to find the electron. And so in quantum mechanics, they say 3 quantum numbers, but there's really, but this is just to describe the distribution of electron density in an atom. They're derived from the mathematical equation from Schrodinger's equation for the hydrogen atom. And so this is n is the principal quantum number, and it's n, and so n, and I call it the energy level. And like I said, these are whole numbers, so n equals, you can't have n equals 0, n equals 1, n equals 2, n equals 3, n equals 4. And so if you're looking at like a hydrogen atom, you have the proton in the nucleus, and then n equals 1 would be here, n equals 2 would be here, n equals 3 would be here. And these energy levels are the levels outside of the nucleus. And so the first electron, because you only have one electron in hydrogen, right? Hydrogen 1 has one proton, it has one electron. In the ground state, it's going to be found in the energy level 1. And so the next time I see you all in class, we will talk about the 4 different quantum numbers, and we will apply that to the atoms models for all the elements. So we'll start looking at all the elements. And this is hydrogen, which has one electron.